Hello, ladies and gentlemen. Welcome to your chemistry class. How are we all doing? Just bring this mic in a little bit closer. Right, welcome. It's Wednesday. That's chemistry day here at TT, and I've got the mic absolutely in the way there. There we go. Get that out of the way. How are we doing? Say hello in the chat, please, guys, because this is going to be really interactive today. I want you guys on it. I want you guys giving me some answers. I want you guys interacting with me, okay? Who have we got? Now, I am on both YouTube and live in our Zoom room. So if you're a subscriber, or if you've got a half-term pass, then you could have registered for this class today. And I'm seeing loads of people saying hello in there. And we got Ariba, Isha, Hafsa, JK, Rabia, Hussein, Yusuf, Tarantima, Ruhab. It goes on and on and on. How are we doing? Isha's been watching my live recordings all day today, like for 8 hours. Oh, that just sounds like torture, to be honest with you. Listen to my voice. The chemistry, on the other hand, spot on, but my voice, maybe not so much. That my North Wales dulcet tones. There we go. Oh, thanks, JK. You know, it's like kind of standard uniform for me and the old band t-shirt. Got AC/DC on today. Ruhab, my voice is stuck in your head. As long as that's not in a weird way, I think that's okay. Who have we got on YouTube? I can see Ronnie's in there helping us out in YouTube. Hey, Ronnie, how you doing? Megan's back, Ishan, Mary, Aman, Dina, loads of people. Absolutely brilliant. The more the merrier here at TT, okay? So first question, I'm going to ask you about how your half-term pass is going. So those of you in YouTube, if you haven't got a half-term pass, you can still get one. Those of you in the Zoom room, then obviously you've got a half-term pass or a subscription. How are we finding it today? How are we finding this week? Hopefully it's been really useful. Myself, Rich, and Ronnie have been talking you through the TT method, how to use the marks I drop sheet, you know, improving your exam technique and stuff. It's really useful. It's really good. It's really useful. It does end on the 22nd, yes, or lunchtime on Saturday. That is it. So that is the end of your half-term pass. We started it last Thursday, so you've got over a week there. So that's why we started early. Questions. So when do you unsubscribe? You do not need to unsubscribe. Your subscription will finish at 12 o'clock on Saturday. And then if you want to start a full subscription for the lead up to your exam, so we can be on that journey with you, then you can do, okay? So make sure that, you know, if you know, I know that obviously it costs money to subscribe. I think, you know, if that's a particular barrier for you, then make the most of this week. Okay, so do what we say, use the TT method, and just get dialed in on that, because you know what, it's still usable without the course. Of course, you get the most out of the TT method, the absolute most, and we guarantee you're improving grade by subscribing, of course. But you know what? This method, it's out there. It's our method, okay? It's copyrighted method. It's ours. That is, you'll not find that anywhere else. So make sure you use it, okay? So Fatima, I can briefly go through the TT method. Now, what I want to do tonight, actually, before I do that, is just let you know what you're in store for tonight. All right. So we're going to be covering some major topics. I've asked, you know, loads of students what we thought we should be doing tonight. So I've come up with a few things. First one, we're going to be talking atomic structure. You're like, oh, atomic structure, we did that in like September in year one. I want to basically open up the whole of the chemistry course to you in terms of atomic structure and why that is so important, and how knowing the underlying principles of chemistry can help you in so many other areas in your chemistry knowledge. Okay, so I'm going to link everything together because chemistry is like a big spider's web of things linked together. So I'm going to do that. Then we're going to go through some calculations. Yay! Like, because that's what everybody asks me for, right? So I've got a foolproof method of doing calculations we're going to walk through with you tonight. And then we're going to look at some practical stuff. I'm going to look at some buffer calculations as well. So yeah, we're going to be looking at loads of different calculations. We're going to look at some easier ones to start with and then work up to some more difficult ones, okay? So it's going to be like year one stuff and year two stuff thrown in there too. So the TT method is basically this, and this is just in a nutshell, guys, okay? You do a paper. Do not think that you leave papers until after you've revised, okay? That is the biggest mistake that students make. Use papers to inform your revision. So you do a paper, you mark it using our marks I dropped sheet, and you analyze it. There's one of three ways that you got a question wrong. Either it was like a frustrating fail or slip, an FFS. So it's kind of like you look at it and go, oh my God, I knew that. Why did I not write that? And you make a journal. Okay, you can't revise that away. If you knew it already, you just made a silly error, then you put it in a journal and you make sure you don't do it next time. The other reason is that is a lack of content knowledge. You just didn't know the answer. Okay, so make sure you understand why you didn't answer that question. And the third reason why you got it wrong is that you didn't understand the question, or you got the wrong end of the stick of the question. Okay, you didn't have the skills to do it. So that's where the TT exam guide comes in to help you. Okay, so analyzing the paper. So you do a paper, you analyze it and mark it, focusing on the marks you dropped. Then you leave it 24 hours and you redo. Then you do 3 hours revision, okay? 3 action hours, we say, based on the areas that you lost the most marks, all right? And using the reason why you lost those marks too, okay? I don't want you thinking, oh, I lost 4 marks in equilibria. Obviously, I don't know anything about equilibria. It might be that you got the wrong end of the stick with the question. You need to practice exam technique. So it's really important you understand why you got the question wrong. So do the paper, mark and analyze, 3 action hours, 3 hours only, then leave it at least 24 hours and do the paper again. Okay, you will see your grade improve, yes, because you've marked the paper. But then when you do, say, if you've done a paper 1, the next paper 1 you do, your initial grade, when you do that for the first time next time, will be higher than the first time round. Okay, so it's really important, and that's your TT method in a nutshell. There are loads of videos on our YouTube site if you want to go and watch those on how the TT method works, not least the ones that Ronnie and I did on Friday and the one that Rich Thompson did on Saturday. So go and check those out. So, right. In terms of what we're doing tonight, I think we should just get started, folks, okay? So we're going to be doing a lot of learning tonight. So the first part, this part about atomic structure, I'm going to be answering your questions. Those of you in the Zoom room, I'm going to be watching that thread there. I'm going to be answering your questions. Ronnie's on YouTube. So if you've got any questions about the course or anything like that, you go ahead and ask Ronnie. You can still, if you've got a half-term pass and you haven't registered for the class and you want to get in on the Zoom room, you still can. So you can still register to get in on the Zoom room with the other people that are already in there. Okay, so if you've got a half-term pass, you can do that. And if you don't know how, then I'm sure Ronnie will help you out. Okay. So I'm not taking any general questions yet, Hafsa. Sorry, I just, I basically asked students what they want to talk about tonight, and this is what we're going to do. Okay. So let's start with atomic structure. All right. So I'm just going to share my iPad. If I can get it to work. Undo. Come on, iPad. I want this to go away. Why wouldn't it go away? 1 second, guys. My bad. Technology always lets you down when you don't want it to. Typical. Right. Okay. So let's go ahead and share screen. So if you are in the Zoom room and you're typing away and you're asking questions, most of the things you're typing are to all panelists. So if you're in the Zoom room, make sure you click the blue button at the bottom of the chat and change it to all panelists and attendees. And that way everyone can see your question and people who are listening to the answer know what question I'm answering. Okay, so make sure you change it to all panelists and attendees. Okay, so what you should be seeing in just a second is my iPad. So my iPad's popped up there. Great. So, okay, so here we go. Boom, we are in, ladies and gentlemen, Chemistry Live class. So atomic structure. Now, I'm going to go through some basics of atomic structure first and foremost. Okay, I'm going to ask you some questions. You guys in the Zoom room chat can be answering those questions for me as well. That's absolutely great. So basic atomic structure. Excuse my rubbish writing. Okay, so what do we need to know? Of course, protons, neutrons, and electrons. Okay, this is really basic stuff, but we're going to start and we're going to build this up. Of course, in the nucleus, we've got our protons and neutrons. They both got a mass, a relative mass of 1, of course. Then we've got our electrons spinning around the outside. We're whizzing through this because, I know we all know this, all right? So the thing is, what we need to know is obviously in a bit more detail. So in each of these energy levels here, we've got orbitals. What letters represent these orbitals, guys? What 3 types of orbitals do we need to know about? Give me some letters. Brilliant. Okay, S, P, D, and there's F as well. But you know what? We don't touch the F. We don't touch the F at A level, okay? So we got S orbitals, we got P orbitals, and we got D orbitals. How many electrons can an S orbital hold, ladies and gentlemen? 2. How many electrons can our 3 P orbitals hold in total? 6. Brilliant. And D? Altogether, 10. Absolutely, okay? So we build up this 1s2, 2s2, 2p6, 3s2, 3p6. 4s2 sneaks in there just before the 3d, okay? So we build up our electronic structure like so, okay? Yeah, I think F is 18. You're absolutely right. I do know F is 18. So we never get to the Fs though, okay? So knowing your atomic structure is very, very, very important. I cannot stress it enough, because what I'm going to show you is that it has a massive impact on your knowledge in, well, not countless other areas in chemistry, in A-level chemistry, but knowing it and understanding the attractions and stuff like that between the nucleus and the electrons, that sets you up for so many other areas in chemistry. And if you've got a tricky question in an exam, you can rely on this basic knowledge to work it out from first principles, okay? So let's have a look at our periodic table first and foremost. So in terms of atomic structure, what can we say about all the elements in, let's say, group 1? What do they all have in common in terms of electronic structure? Let's just simple things to start with. Yeah, 1 electron in the outer energy level. Absolutely. What orbital is that outer electron in? What type of orbital is that outer electron in? Good, because it's S block. Absolutely. Same for group 2. So whatever the group number is, that's the number of electrons in the outer energy level. Same over here. We've got our P block, of course, and we've got our D block here. Okay. Now, going across a period, just in terms of trends now, what happens going from left to right across a period in terms of atomic radius? So we got increases, decreases, increases, stays the same. It is decrease, ladies and gentlemen, okay? Now, this is part of the reason, right? You don't just learn that fact that it decreases going from left to right. What you need to do is understand why, which is really, really important. So all of these have the same, going across any period, they have the same shielding, okay? So they have the same number of energy levels. But what is increasing going from left to right? Good. Who said that issue? More protons, add on more protons. Absolutely. So more and more protons as you go across, just adding a proton each time. So if the electrons are the same distance away, if you've got more protons, what's going to happen to those outer electrons if that nuclear charge is increasing? They're going to get drawn in. They're attracted more strongly. So what we actually see in terms of atomic radius going across is that this is the biggest, that's slightly smaller, 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 okay? Because of increasing nuclear charge, same number of energy levels, so increasing nuclear charge draws those electrons in, okay? So a greater nuclear charge means a greater attraction to the electrons that are orbiting it, okay? So that's really, really important. What about atomic radius going down the group? What happens there? Does it increase or decrease? Increases. Good. Okay. This time we've still got, in this case, a massive increase in nuclear charge, a massive increase in nuclear charge. But the thing is, what else is also increasing? Yeah, Hussein's already said it. Shielding. Absolutely. You are adding an extra energy level each time. So as you go down, these are going to get massive going down there because we're adding energy levels. So knowing your way around the periodic table in terms of electronic structure, in terms of the trends and things is massively important, okay? Now, speaking of attraction, one of the first things you do in A-level chemistry is learn about ionization energies, okay? So we're just going to look at first IEs right now, okay? So there are 3 things you need to know. Down a group, excuse my rubbish writing, what happens to first ionization energy down any group? Decreases. Absolutely. Guys in the Zoom room are absolutely smashing it tonight. So it decreases down a group. Now, the big question is why? There are 3 things we need to say here in terms of our explanation. It's an absolutely stock answer, okay? So what's one of those things we need to say? I'm going to keep an eye on the chat. less energy. Well, yes, there's less energy needed. It's not a reason why there's less energy needed, though. Decrease in electron shielding, greater in electron shielding, more shielding, electrons further away. Yeah, absolutely. Okay, so first thing, the reasons are increase, okay, in distance of outer electron from the nucleus. Okay, we also, that means, have an increase in shielding, and that means there is a weaker attraction between the nucleus and outer electron. Okay, that's really, really important. So what we get is, it's like putting, it's like you have two bar magnets together, and they're attracting north and south, they're attracting, and that's fine when they're close together. But if you put like a big thick textbook between them, okay, that's like shielding. It's the attraction between those two things is less. Okay, now Ruhab, you're absolutely right. This is what I call the drop the mic statement. So therefore, less energy needed to remove that outer electron. Okay, because why does it take less energy to remove the outer electron? That's usually the question. So you need to mention energy in your answer. Okay, Yasmin nailed it, absolutely nailed it. That's perfect. So if anybody wants a stock answer that's presented a little better than mine right now, check out Yasmin's answer. Okay, so that's down a group. So what we can say is this, okay, stock answer. If I asked you, okay, why does rubidium have a lower first ionization energy than potassium? That, ladies and gentlemen, will be your answer, okay? Because it's got an increased distance between the nucleus and the outer electron, therefore increased shielding, therefore a weaker attraction between the nucleus and outer electron, and therefore less energy to remove. So literally any two that are in the same group, okay, indium and aluminium, you can use that same answer for. So as long as they're in the same group, you can use that answer. Maybe they've switched the question around and said, oh, why is aluminium higher than indium? Well, you just flip your answer, okay? So that's all it is. Going across a period, it's different, isn't it? Okay, so going across a period from left to right, what we have here is what's our general trend? What's our general trend, first of all? Yeah, general trend is an increase, okay? Generally from left to right, okay? So it's an increase. The reasons, again, so we have got an increase in nuclear charge. We have got the same shielding. Therefore, obviously the same distance. I mean, there's a smaller distance, isn't there? Because we just said atomic radius is getting smaller. So decreased distance, we could say, okay, we don't have to put that. It's kind of like a, yeah, it's true, but don't worry about it. So therefore, attraction, you got to mention attraction is greater or stronger. So therefore, more energy is required to do it, okay? So we have got some exceptions as well, haven't we? It doesn't just go up like this across the period. It kind of goes up and then down like so. Okay, we've got some exceptions. Now, I'm not going to go into those right now because I want to show you about atomic structure and its links to everything else in chemistry. But we do need to know the details about those. In terms of details about SPD orbitals, the same, that you should only ever mention orbitals in your answer in terms of ionization energies when it's these exceptions, okay? So between groups 2 and 3, and so yeah, between the groups 2 and 3 and 5 and 6, okay? So that's the only time you should be mentioning orbitals and pairing of electrons and orbital shielding and things like that, okay? So, so our exceptions are between beryllium and boron and nitrogen and oxygen. So 5 and 6, so 3 and 4 and 5 and 6. There are exceptions, okay? So that's it. So for beryllium and boron, magnesium and aluminium, the reason for the exception is the same. For nitrogen and oxygen and phosphorus and sulfur, the reason for the exception is the same between those two sets, okay? So just be aware of that. So that is ionization energies in a very, very tiny nutshell. But what we need to do is link this knowledge that we have of nuclear charge and shielding and attraction to the other areas that it becomes important in chemistry. And this is what I want to do by linking all these things together for you, okay? So that's ionization energy. So that is number one, okay? So I'm going to go back actually to this so we can actually make a note of all the things that atomic structure and a good knowledge of atomic structure and shielding and attraction and stuff. So ionization energies is number one. Number two, and this is in no particular order, redox power. Okay, now let's take our halogens. Okay, so we've got F2, Cl2, Br2, and I2. Okay, now we talked about reactivity before. Okay, now in terms of reactivity, which is the most reactive halogen? Yeah, fluorine, absolutely. We learned that at GCSE, but they react. That's a bit of a dirty term now, isn't it? What actually happens to them in terms of redox? When these halogens react, what happens to them in terms of redox? They gain electrons. They are oxidizing agents. Absolutely, these are oxidizing agents. Okay, so what they do is they take electrons from other things. Now, I want to ask you, why is fluorine the strongest oxidizing agent here? Why is, bearing in mind what we were talking about 2 minutes ago, why is fluorine the strongest oxidizing agent? Ruhab, nucleus, strong to ionize, strongest nuclear attraction, least shielding. Yeah, absolutely. So because fluorine, okay, is in period 2, it's only got, it's got very little shielding. Okay, so it's really good at attracting an electron to it. Whereas iodine, down here in period whatever it is, it's got loads and loads of shielding, and it's got its nucleus, and yeah, it's got more protons, but all that shielding, all that buffer it's got around it, it's absolutely dog poo attracting electrons. It's the weakest one. You see the link, the knowledge of atomic structure and why that's important, okay? Now, you can do this with any elements. You can say, oh, why is this element a stronger oxidizing agent than that one? Well, it's because of shielding, decreased, attraction of the nucleus to the electron, and so on and so forth. Okay, so that's, don't just learn things off by heart in chem. It all stems from its fundamentals. So what about halides? Okay, so we've got F minus, Cl minus, Br minus, and I minus. Which of those? These are all reducing agents. Okay. That means they give away an electron. They can give an electron to something else, reducing it, okay? Which is the strongest reducing agent? Yeah, I minus is the strongest. Why is I minus the strongest? Yeah, again, because of the increased shielding. Fluorine here, okay, let's say it's gained that electron. It's got 8 electrons there. Because of that strong nuclear charge and relatively strong nuclear charge and low shielding, once fluorine's got hold of that electron, it ain't letting go. It ain't letting go. Whereas with iodine, it's kind of like, look at all that shielding there. It's got these electrons, and this one is the one it's gained. Something comes along that's vaguely good at accepting electrons, iodine is going to be like, yeah, have it, whatever. I can't hold on to it. It's like it's holding on to it with its fingertips. All right. So again, the reason why iodine is the strongest reducing agent, iodide is the strongest reducing agent, is because of all the shielding, and it just lets go of that electron. Whereas fluorine, no, holds on to it. Really rubbish at reducing things. So that's the reason why. Okay, so that's our second thing. So the importance of atomic structure, linking it to redox power. Okay, and you know what? We can link it to metals as well, right? What about the reactivity of group 1 metals as you go down? That increases. Why, pray tell? And it's the same reason. Why is francium, whatever you want to call it, the most reactive, i.e. the strongest reducing agent there? Yeah, not less nuclear charge, but because of increased shielding, it's got a lower effective charge, we say, really. So it just lets go of its electron. It's like, yeah, fine, have it, whatever. So for the same reason, iodide is the strongest reducing agent on the other side of the periodic table, francium is the strongest reducing agent of all these metals on the left-hand side. Okay, and you can figure that, you can see this as well. Those of you doing year 2, doing electrochemistry, and you see all your half equations and stuff, and you got your order of E0 values, it all links to that too. Okay, what's the strongest reducing agent? What's the weakest oxidizing agent? So on and so forth. Okay. No, don't worry about reactivity and redox power and stuff like that in metals. Nothing to do with the fact that electrons are delocalized. Nothing at all. Okay. So that's number 2. Number 3, okay, and we are flying through here. I'm just going to go back to this. Number 3, I've got written down here in my little cheat sheet, is electronegativity. So what about our trend, ladies and gentlemen, in electronegativity? Let me just tidy up my rubbish that I've got all over this periodic table. What's our most electronegative element? Fluorine, absolutely. This bad boy up here, okay? Now, the definition, I'm not going to ask you to type it out because that'd just be really mean, but the definition of electronegativity is the ability of an atom to attract a bonding pair of electrons in a covalent bond, okay? What do you think actually dictates that? Well, it's the charge in the nucleus, right? And it's the shielding around that atom. So fluorine, again, okay, why is that the most electronegative? Well, for the same reasons as here, okay? Very little shielding. Its nucleus is really close to that bonding pair of electrons. So let's say you've got fluorine bonded to, I don't know, hydrogen, let's say for argument's sake, okay? Now, and compare that to hydrogen bonded to iodide, okay? Now, fluorine has got very little shielding. Okay, so we've got a little F here and we've got very little shielding there. So this nuclear charge for fluorine is going to attract these electrons really, really easily. Okay, it doesn't mean it has the highest nuclear charge. No, it's actually got the lowest nuclear charge of group 7 because it's right at the top. But I know you get an increase in nuclear charge. The number of protons increases massively going down a group. But the shielding on top of it actually means that the nuclear attraction is weaker, okay? So you might have more protons as you go down the group, but the extra shielding actually means effectively that nucleus is less good at attracting things towards it because of all the shielding around it, okay? So the strength of fluorine's nuclear charge, the relative strength of fluorine's nuclear charge is greatest because of the lack of shielding around it. Okay, so it's like really good. It's like having a bit of paper between 2 bar magnets instead of like 3 textbooks. If that makes sense. Okay, my rubbish analogy there. But we've got iodine. Okay, even though it's got a greater number of protons, you've got all this shielding going on around it. Okay, and it's less good. I mean, all of this buffering here, all this shielding is just preventing from those electrons being drawn towards that nucleus. So it's not very electronegative at all. So again, we come back to trends in nuclear charge and shielding and so on and so forth. Okay, so that's the reason why we have different electronegativities for different elements. Okay, so that's why these 3 bad boys up here, if I can highlight them, NOF, are the highest, are the most electronegative elements. Okay, they are the most electronegative elements. Okay, Matilda, it's the inverse square law. A strong nuclear charge far away has less effect than a close weak charge. Yeah, it's inverse of that. Yeah, it's the inverse of that. Okay. So even though it's a strong one that's far away, it's less attractive to those electrons. So if you're ever wondering, okay, in terms of electronegativity, why one's more electronegative than the other, and you might be asked that, then your reason is down to atomic structure. Okay. This is on for 2 hours. 2 hours. We're on until 8 o'clock if my voice holds out. Okay. So going back to, oh, come on. There we go. Going back to this. Now, I think electronegativity, when we think electronegativity, what topic does that lead us on to next? Bonding, absolutely. Intermolecular forces and bonding and stuff like that. So in terms of bonding, okay, and well, no, so we do bonding first, okay. Let's think about bonding. I'm going to get rid of this, save wasting a page. Now, of course, we were taught at GCSE, what sorts of elements do you need to create an ionic substance? Metals and a non-metal, okay? Almost. Okay, we look at our periodic table and it's like, okay, take one from the left and one from the right, and then we make an ionic substance. That's fine, okay? But let's just think in terms of electronegativity, all right? AlCl3 is a metal and a non-metal, but that is actually covalent, okay? It is a covalent substance, aluminium chloride. The reason? Well, if you look at the electronegativities of aluminium and chlorine, they're actually very, well, not very similar, but they're actually quite close together. So aluminium's not ready to kind of let go of its electrons completely. Chlorine's kind of like trying to get those electrons from it, but not quite, okay? Very good knowledge, you should, aluminium's amphoteric. So in terms of bonding, atomic structure plays a big, big part in that as well. Okay, if you've got a group 1 metal like lithium or sodium or potassium, their electronegativity value is quite low. They're really rubbish at holding on to electrons, basically. And if you take a halogen like fluorine, chlorine, or bromine, then yeah, you're going to get a full transfer of electrons, complete transfer of electrons from one to the other, and it's going to be ionic. But the thing is, a lot of substances, there's a lot of gray area in there, and it comes down to atomic structure again, whether it's covalent or ionic. And those of you in year 2 know that, or you should know by now, that, oh, it's Easter. Sorry, I do apologize. Yes, let's focus. All right. So in terms of the type of bonding you see, it does come down to atomic structure again. Okay, it really does come down to atomic structure in terms of bonding. Okay, so the perfect ionic model. Okay, some ionic substances have covalent character, so they don't perfectly transfer electrons and then they stay where they're put once you formed your ions. Sometimes they like flip over and have a little bit of covalent character. Some covalent molecules have a little bit of ionic character, and again, it all comes down to electronegativity and the draw that those atoms have on those bonding pairs of electrons, okay? Or those, yeah, like in lattice enthalpy, Miriam, you're absolutely right, like in lattice enthalpy. So when you talk perfect ionic model, the reason for things having some covalent character, again, it all comes down to shielding, it all comes down to, you know, relative nuclear charge or effective nuclear charge and so on and so forth. But moving on, I think that the biggest thing that probably springs to people's minds is what we mentioned just a minute ago, and that's intermolecular forces, okay? Intermolecular forces. I believe, Ella, it's a very good question. EdXL, Ella's asked, do we get a Pauling scale chart? EdXL give you a Pauling scale chart. OCR and AQA, if they want you to use Pauling values, they'll give them you in your question, okay? So in terms of intermolecular forces, what's the upshot of that? Well, of course, it dictates whether something's got a dipole or not. That's what electronegativity does. So if you've got something like chloromethane, okay, because chlorine is more electronegative than carbon, we end up with this dipole, okay? And this bonding pair of electrons gets drawn more towards the chlorine. And then that dictates the fact that, well, what intermolecular forces would this have? Yeah, permanent dipole. So I'm just going to go dipole, okay? Of course, what else we need to be able to spot is what is essentially just what I call like a super dipole, okay? Hydrogen bonding, absolutely, okay? So we get hydrogen bonding here because, well, why? Hydrogen bonding is nothing magical. Hydrogen bonding is not like a separate intermolecular force all on its own. Well, it's classified as that, but really it's just another dipole, because what we've got here is oxygen is one of our top 3 NOF, highly electronegative elements. Okay, JK, it is like a glorified dipole. You're absolutely right. So what it does is it's really attracting that pair of electrons towards it. Now, hydrogen, of course, it only had one electron to start with. So if you've got oxygen here, okay, with all of its electrons, okay, in a bond there, and this is the pair it's sharing with hydrogen, what's left over here with hydrogen is just a proton. It's like a naked proton, okay? So the naked proton is really, really positively charged. So like I said, this is kind of like a souped up dipole. That's all hydrogen bonding is. And that's why you only ever see it when hydrogen is directly bonded to a highly electronegative element. So nitrogen, oxygen, or fluorine, okay? So that's what we get in terms of atomic structure, and it's linked to intermolecular forces. Now, if you're ever looking for, you know, what intermolecular forces are present between certain molecules, then you can rely on the fact that, okay, well, I know that these are the most electronegative, and I know why these are most electronegative, and therefore that will lead me to understand what intermolecular forces are actually present. Word to the wise, ladies and gentlemen, in terms of hydrogen bonding, okay, there are only it's a very short list of molecules that will show hydrogen bonding. Okay, so we've got hydrogen fluoride, standard. We've got ammonia, because it's hydrogen and nitrogen. And of course, we've got water. But in terms of organic chemistry, things that show hydrogen bonding are anything with an OH in and anything with an NH in. Okay, so it could be an amine, it could be an amide, it could be an alcohol, it could be a carboxylic acid. All right, that's basically a very short list of things that show hydrogen bonding, ladies and gents. All right, very, very short lists. Okay, so hydrogen bonding can happen between molecules, absolutely. Okay, and what's really important is if you have, let's say, for example, let's say you had some water here, so delta positive, delta negative, this would be considered, this here would be considered a hydrogen bond, because you do not need two molecules that have an OH or an NH or an FH. You do not need to have two of those. As long as you've got a dipole in one, just a regular dipole, and one of the molecules has an OH, an NH, or an FH, then that is considered hydrogen bonding. That's really, really important, that, guys, okay? So what's the bond between hydrogen and carbon in organic molecules? It's just a regular covalent bond. It's actually a sigma bond, okay? A sigma bond, which is really important, okay? So that is intermolecular forces in a nutshell. We are flying through, ladies and gentlemen, okay? So I'm just hoping that you understand the links between all of these things, all right? Now, let's look at rates, okay? There is a very specific example of rates, okay? Now, let's say I took this molecule, I'll tell you what, let's change this up. And this molecule. This one is Cl, Br, and I. Now, they can all be hydrolyzed. Yeah, okay, Yasmin's ahead of me. They can all be hydrolyzed, okay? They can all be swapped out for an OH. It's basically nucleophilic substitution. It's a year one thing, okay? All of these have got a dipole on. And as Yasmin's just already said, that this one at the bottom down here hydrolyzes the quickest. It is the easiest to hydrolyze. It has the fastest rate, okay? Just to go back to that, okay? What I was saying is if you've got two molecules, one is just dipole, and the other one is like water or ammonia, something that could show hydrogen bonding, and you've got a link between them, that is known as a hydrogen bond, okay? So you do not need two water molecules or two ethanol molecules. So if you have a regular dipole in one molecule and the other molecule shows hydrogen bonding, then the attraction between those two things is considered a hydrogen bond. That's what I meant. So back to this one, somebody's already nailing it in here. Why does this one have the fastest rate? Well, it's not down to the dipole. Which of these is the strongest dipole, guys? Yeah, the Cl, absolutely. Again, smashing it tonight. The Cl's got the strongest dipole. In fact, your nucleophile, let's say it is an OH minus, will be more attracted to this one than the others. Okay, but the thing is, when it gets there, it just can't do anything because the bond is so strong. It's got a high bond enthalpy. It requires a lot of energy to break that CCl bond. Okay, but the thing is, so that can't be the deciding factor on which gets hydrolyzed the easiest. The deciding factor is the bond enthalpy. So whilst this is the weakest dipole, the Ci is the weakest dipole, when your nucleophile gets there, it's actually the easiest to break. Now, can anybody tell me why it is the easiest to break? Why does that Ci have the lowest bond enthalpy? Hamdan, you're absolutely right. Sorry, I'm just looking again below that, the fundamentals at the bottom of it. So why does that have the lowest bond enthalpy? Good. Issa's on it, Hussein's on it. Well, we're not, careful, Ruhab, we're not removing electrons here. Okay. So if we take, let's say this is the C atom. Okay. And let's say this is Cl. Okay, and there's our nucleus for Cl. You can see this overlap. There's very little distance between the Cl and the carbon there, okay, because of the atomic structure, because of the lack of shielding. Whereas if we take carbon down here, and we have got a massive iodine molecule, okay, and let me just change my pen color. This attraction here is a lot further away. The overlap of electrons here, okay, is a lot further away from the nucleus of iodine. It's kind of like just holding on. Its outer electrons are over here, just kind of sharing and overlapping with the s orbital of the carbon atom. So actually, that's why it's got the weakest bond enthalpy, because again, all right, we've got all that shielding. The attraction between the nucleus and that pair of electrons is really, really weak. So when something gets there to break the bond, it's kind of like, yeah, have it, whatever. Iodine's just like, I'm over it, whatever. All right. So again, this comes down to atomic structure. Okay. So it all comes down to atomic structure, the fundamental basis of all of this. All right. We are flying through, as I keep saying. We're going to move on. There's something else I want to tell you guys about. So what about, I mean, let's go shapes of molecules. I'm not going to go into this one too much because it's kind of obvious. So in terms of shapes of molecules, okay, knowing how many valence electrons, so how many electrons are in the outer energy level, that dictates the shapes of the molecules and things. So I'm not going to go into that. It's kind of obvious, lone pairs and bonding pairs and so on and so forth, okay? Next up then, that I am going to talk about in more detail is organic chemistry. Okay. Now, in terms of organic, there are a couple of things I want to mention. Number one, mechanisms. Okay. Now, this is fundamental. They may give you molecules. In fact, you know what? They will give you molecules you've never seen before and ask you to do a mechanism for it. Okay. So the thing is, we've got to figure out what the mechanism is. So if in order to figure out what the mechanism is, you need to know exactly where all your lone pairs are and things like that. So knowing that oxygen has got two lone pairs there, we've got that bond angle in there because of the two lone pairs. And we've got, let's say, you know, this molecule again. In fact, I'm not going to do that. I'm going to do water. Like so. Ooh, my Alexa's listening. What type of mechanism is going to go on here? Nucleophilic substitution, absolutely, okay? So you need to spot where the dipoles are based on electronegativity, based on atomic structure. And again, you're going to see these dipoles. So what's going to happen here is that this part of the molecule here is going to be attracted. No, sorry, tell a lie. This part of the molecule here, I'll put this in red, is going to be attracted to your delta positive carbon, and it's going to break that bond. Okay, so it's about movement of electrons, it's about your dipoles, it's about lone pairs, it's about full charges. Okay, Ella, there isn't a mechanism cheat sheet on the website. That's not a bad idea to put something like that in there, but I'm not a fan, and in fact, I highly recommend you don't just learn these mechanisms off by heart. Understanding them as well is really, really important. So drawing them out yourself rather than just printing a load out is really more helpful than just having, say, a bunch of flashcards with them on or something like that. So, you know, you got to actually practice these and, you know, use the exam papers to look at the types of things that they could ask you for mechanisms for. AQA are particularly naughty when it comes to giving you mechanisms that you have to kind of figure out yourself. Okay, so understanding, you know, where your electrons are going from and to the potential for attraction between something that's delta negative and delta positive and that's got a lone pair and so on and so forth. Okay, so that's really, really important. Okay. Yeah, I could do something like that. I've got 1,000,000,001 things to be doing for you guys that we've already got in the pipeline at the moment. Doing my best. All right. So yeah, there's so many things I want to put on the site, but there's only one of me. So there we go. We're getting there. So that's mechanisms. The other thing I wanted to say in terms of organic chemistry is second years, you need to know about amine bases. No. Let's not do that. Let's not do that. Let's do Markovnikovs first. Okay. So where you get carbocations. Okay. So we've got this one here. And let's say, bear with. Which of these two carbocations, the one on the left or the one on the right, is the most stable? This is a year one question. We got right, we got left, we got one, we got right, we got left. Right. Sorry, I won't say right. It's this one. This one is the most stable. This is what's known as a tertiary carbocation because it's got 3 alkyl groups around it. There's no hydrogens attached to that positive carbon. Whereas there are 2 hydrogens attached to this one. This is a primary carbocation. In terms of relative stability, tertiary is more stable than a secondary, which is more stable than a primary. Okay. Now, the reason for it is what? Is anybody? Oh, Tima's already in there. Positive inductive effect. Okay. Positive inductive effect. So what that means is that in terms of atomic structure, you know how we have highly electronegative elements that draw electrons, bonding pairs of electrons towards them? What do you think elements that don't have a high electronegativity value do? Donate electrons. They're quite good at pushing electrons away from them. Well, they don't physically push them away, but they let them go very, very easily. Okay. So these electrons actually migrate towards, from the carbons towards that positive charge and kind of like, you know, put their arm around it. It's okay. I know you're really positive right now, but we'll look after you. It's all fine. Whereas over here, the only place that those electrons can come from is here because this is bonded to 2 hydrogens and 1 carbon. So that's why. Okay. So the primary carbocation is less stable because of that inductive effect. Okay, it's got less carbons to give it that positive inductive effect and give it electrons to make it stable. Secondary, it's got 2, it's a little more stable. Tertiary, it's got, oh, I've got 3 mates here, all giving me electrons, making me nice and stable. Okay, so again, it's like the opposite of electronegativity. Carbon alkyl groups are really good at like, yeah, you know what? If something's attracting those electrons away from me, that's absolutely fine. Okay. Now, JK, basically, yeah, you're going to hate me for the pun, but let's talk about bases. Let's talk about this second years. Okay. So what about this? Which of these is the strongest base? In fact, I'm going to put another one on the end there. Which of these is the strongest base? Which of those is best at attracting a hydrogen ion? We got right, left. They're the same. This one. Bearing in mind what we've just said, carbon's electrons can have a positive inductive effect. Nitrogen here, whilst it's not got a positive charge, nitrogen's one of our top 3 electronegative elements, right? So what's happening here is that, okay, this carbon can kind of provide electrons, a positive inductive effect, making this even more delta negative, okay? And that's fine. But the thing is, the more carbons we've got, the more delta negative this nitrogen is, and then the more attractive that lone pair is to a proton, a passing proton, okay? They're both primary amines. Yeah, absolutely. They're both primary amines. Okay. But the thing is, because of this long carbon chain here, it's got a greater positive inductive effect. Okay. So more carbons, basically, there's more carbons there to kind of provide it with electrons to make it more attractive. Okay, so the nitrogen is kind of having this pull on the electrons, but the more carbons are there, the more it can. It's true as well for like tertiary amines are better at it as well. So if I was to look at a primary, secondary, and tertiary amine like so if we had this one, okay, for the same reasons as above, we have got this positive inductive effect making this tertiary amine a really strong base. Okay, really strong base. Whereas if we had a primary one, it's less so. Okay, so for exactly the same reasons, these two things are linked. They're not completely separate. Okay, the same reasons apply to both of them. Okay, and Issa, yes, absolutely. When you're looking at phenylamine, like so, the opposite is true. That lone pair of electrons on nitrogen, it kind of gets sucked into the benzene ring in terms of those delocalized electrons, and it's a rubbish base. Okay, it's a rubbish base. Okay. Now, speaking of benzene rings, the other thing I wanted to say, some of you, not all of you, need to know about electron withdrawing and donating groups in terms of a benzene ring. Again, that comes down to like electronegativity, doesn't it? How good are they at holding on to those electrons, or how good are they at attracting electrons to them? Okay, so you need to know that. Some of you, I know edX, I know OCR need to know it. Yeah, I don't think AQA need to know that, but it's all part of atomic structure. So I'm going to add that. I'm going to add organic. I'm going to add Markovnikovs. I'm going to add amine strength or amine base strength. And I'm going to go with electron withdrawing and donating groups. So it all comes down, let's not forget, atomic structure. How good are they at attracting electrons or releasing electrons? That's what it all boils down to. I'm going to stop there. Now, we are going to do some calculations very shortly, but I want to ask you, I mean, have you learned something here? Just a simple yes or no. Brilliant. We go, yes, 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 yep, 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 yep. Brilliant. Okay. Because very rarely, and there's some amazing teachers out there, absolutely amazing teachers, but very rarely do we get the chance, because I know I used to work in college, like for years and years and years, do we get the chance to actually sit down and go, right, let's pull all these things together. What have they all got in common? We cannot teach chemistry as completely separate individual things that you need to know, because it is a spider's web and everything links together. Okay, so linking things together is massively important. Okay, and that's one thing I try to do in the course as well, in the content guide. You know, this links to that links to that, and so on and so forth. But just putting it all together, having that fundamental foundation, that baseline knowledge of atomic structure, the first thing that you guys learn when you walk through the door in September in year one, how important is that? How important is that to understanding why everything else works? Okay. That's Miriam. Thank you very much. I've always taught them as separate, and this just shows how easy it would be if you link them together. Absolutely. Okay. You can probably count on one hand the number of fundamental chemistry principles that you need to actually understand why everything works the way it does. Okay. So electron withdrawing and donating groups is the last bit there. Okay. So I'm just going to take a sec to stop talking because I've been rabbiting for ages so quickly. Right. Now, if I just grab something on my, where are we? Oh, I've lost the tab that I need. That's not the one I want either. Right, I've got a link for you guys. Yeah, Miriam, you can watch this live again. It's going to be on YouTube, and we're going to put the recording up. Here we go. We're going to put the recording up in there as well, just like every live class that we do. Now, we're moving on to some questions. You guys are going to have to get your calculators out, right? Because we are doing some questions. So hold the chat in the Zoom for a second, guys. Don't type anything because, boom, there's a link there and you can download the PDF that I'm going to be using in a second. Those of you watching on YouTube, you can download the PDF. It is in the description, ladies and gentlemen. It's in the description. So make sure that you get that. If I can bring you back, I need to find my YouTube. Where's it gone? So many windows. No, it's not that one. Where's my YouTube gone, people? Where have my YouTube people gone? Tell you what, here we go. I can see you. We're back again. We're back again. I think. Sorry, guys. I'm just trying to. There we go. I'm in. So, like I said, YouTube, link to the paper is, link to the PDF is in the description. Those of you in the Zoom chat, I've just put it in the Zoom chat. Everyone download that, okay? JK, I've just skimmed through it and it's not all AQA. Do you think I live to serve AQA? All right. There are other exam boards out there. It's like BBC in it. Other exam boards are available. You know what? I mean, you know, there's WJEC, there's CIE, there's international levels, there's the OCRB, there's the Scottish ones. You know, there's so many out there, okay? But we're focusing on the big three at the moment. All of these questions come from the big three. Now, two things, okay? One, yes, we're focusing on calculations and some practical skills as well. And we're going to be doing some buffer calculations in the next hour. The second thing is I wanted to show you that these questions, especially calculation questions, do not be afraid of using the curated papers in the exam guide, especially for big calculation questions, all right? Because mole calcs is mole calcs. I don't care what exam board you're doing, mole calcs are mole calcs, all right? So do not be afraid of stretching your revision if you need more questions to the other exam boards in that respect. But again, use the curated papers in the exam guide because we've done the hard work for you. You don't have to worry about whether it's going to be appropriate or relevant to your exam board, okay? So let's bring up that PDF, shall we? Boom. Okay, so we are going to look at some, we're going to do two things. This is multi-aspect this, okay? We're going to look at a technique for mole calcs, and we're going to look at some practical based questions as well, because you know as well as I do that the practical style questions are in the exam. Why do you rinse that burette out? What do you rinse the burette with? How do you make a standard solution? The practical questions are really important, and knowing your pracs is really, really important, okay? So let's do, I'll tell you what, let me talk you through my basic attack for mole calculations, all right? Now you're going to like this, okay? So every single mole calc is 3 steps. I don't care whether they're worth 3 marks or 7 marks. There are 3 steps, basically. Number 1, find the number of moles of something. Okay, let me try and simplify these for you because they can look dead scary. Find the number of moles of something, all right? You will have means to do that, whether it's mass over molar mass or concentration times volume. That's it, okay? It doesn't matter whether it's a big old redox calculation or a simple titration or mass calculation. Number 2, stoichiometry. Okay, basically your ratio. So don't forget, if you've got an equation, if you find the number of moles present of one of those things, whether it's a reactant or a product, you know the number of moles of anything else in that equation. All right. So find the number of moles of something in an equation, use stoichiometry to find the number of moles of whatever it is that you need. Okay. So basically find the number of moles of what you need. All right. That's the second thing. Number three, you got that number of moles of something you need. You might need to do a little bit of jiggery pokery here, but essentially you can turn that number of moles into a mass, or you can turn it, you can find the MR of something, you can find the concentration of something, you can find the volume of something, okay? Or maybe it's a percentage by mass, okay? Or something like that. Once you've got that number of moles of magnesium or ethanol or whatever it is in the question, you will have the information to turn it into whatever the answer of the question needs to be, okay? So any single mole calc question are these three steps. Find the number of moles of something, use a bit of stoichiometry to find the number of moles of whatever it is you need, then turn it into whatever it is you need, okay? Yeah, grams per decimeter cubed included, okay? Grams per decimeter cubed included. You know, turning moles per decimeter cubed into grams per decimeter cubed is easy. Can you turn number of moles into grams? Can you turn moles, number of moles, sorry, mass equals number of moles times molar mass? Okay, just forget that it's decimeter cubed, just turn moles into mass. That's how you get to grams per mole, grams per decimeter cubed. All right, that's all it is. Okay, yeah, times MR times molar mass. Yeah, absolutely, that's it. So those are the three steps. This is a technique now, and I want you to, I'm going to work through this technique with you, okay? Now, when you get a mole calc, all right, and you're practicing these big titration questions and what have you, do not just dive in, especially in your exam. What you want to do is practice now how your roadmap, your route through the calculation, okay? Just diving in and it's like, all right, well, I can find that and I can turn that into that, and like just struggling on through with all the numbers. Don't do that to start with, okay? I want you to decide on the path through, okay? I'm going to show you what I mean by that, okay? So let's bring this up, okay? So everyone's got access to this. So ethane dioic acid is a diprotic acid. Beekeepers use it as a pesticide. Student carried out a titration with sodium hydroxide to determine the mass of the acid in solution, okay? The student repeated the titration until concordant titers were obtained. The student found that 25 centimeter cubed of this ethane dioic acid reacted completely with that volume. So that's our mean titer, and that concentration of sodium hydroxide. Calculate the mass in milligrams of the acid in 25 centimeter cubed of this solution, okay? So some people have already got the answer to this, and that's absolutely fine. But this is what I want you to do, okay? I want you now to make a roadmap. I'm going to do it together. What is the first thing that we need to find out here? What's the first thing that we can find out here? Yeah, good. So number of moles of NaOH. And how am I going to do that? What equation am I going to use for that? Concentration times volume. So I'm going to write number of moles of NaOH in my mean titer, and I'm using concentration times volume. Good. What's the next step? Your roadmap. Where's your roadmap? What's the next step? The ratio. Good. Okay. So ratio, your stoichiometry, and that gives you the number of moles of H2C2O4 in 25 centimeter cubed. Okay. That's your ratio, stoichiometry there. What's your next step? Find the mass. So then we can find the mass of H2C2O4 in grams using number of moles times molar mass. Okay. Now, of course, we need to do a bit of what I call jiggery pokery at the end here, because what's the last thing we need to do? Yasmin, on it like a car bonnet. We need to times by 1,000 to turn grams into milligrams. Now, this is three steps, the three steps that I told you about. Of course, yeah, a little bit of jiggery pokery to get your fourth mark there, but that's that. So who got an answer for this? And you put your answer in? Anybody get an answer to it just yet? Pop it in the chat for me, guys. 593, 569, 569, 593. There's some differences of opinion here, okay? I can tell you that the answer is 569 milligrams, okay? 569 milligrams, okay? There's one I did earlier just to my left-hand side, okay? So 569 milligrams. Now, this practice in making a roadmap for yourself, when you get a big calculation, I cannot stress how much more useful it is when you get a big 6 or 7 marker. Those of you doing A2 or A level know that there are big 6 and 7 mark calculations out there. Give yourself a roadmap. It'll take you like 2 or 3 minutes, but then you're not going to lose yourself through those calculations. So that is my kind of bombshell of a piece of advice for you tonight in mole calcs. All right. The 3 steps, and do yourself a roadmap. Okay. In fact, you know what? Anybody in the exam guide seen me do this? Anybody seen me do this in the analysis videos in the exam guide? Yeah. Brilliant. So that's what I'm doing. I'm thinking about it before I put pen to paper. It's like planning an essay. You wouldn't start writing an essay without actually having some sort of plan first. And that's what I do with the level of response questions as well. Okay. He said 8 hours of it. Yeah. So that's what I do. And I want you to practice that. But before we move on, question. The student used a wash bottle containing deionized water when approaching the endpoint in the conical flask. Why does this improve the accuracy? Now, these are practical questions. So to ensure all the acid reacts with the alkali, to ensure it all titrated, to ensure all reagent is transferred so it can react. Yeah, absolutely. I think we've got it essentially. So you got reactants that may splash onto the side on the inside of the conical flask. The rinsings ensure that all reactants are present in the reaction mixture. That's what we need to say there. So that all reactants are present in the reaction mixture. Now, give the meaning of the term concordant titers. What is the meaning of the term concordant titer? Yusuf, first through the gate there. Good. They need to be within 0.1 centimeter cubed of each other. Okay, they need to be within 0.1 centimeter cubed of each other. That's all you need to say for that question, folks. Okay, so these are the types of little follow-up questions, these little niggly questions that they put on the end of these titration style questions. Okay, so we're not going to do any more on that one. Let's move on to another one. Let's move on to, I'm just thinking of time here, guys. Let's do this one. This is a tricky one. So let's read through it, and I'm going to talk about doing a roadmap for it. Okay. So compound B is an iodate 5 salt of group 1 metal. The iodate ion is IO3 minus. A student carries out a titration to find the formula of compound B. All right. So we need to find the formula of compound B. Now, what's the formula of compound B going to be? If M is our metal, what's the overall formula going to be? Bearing in mind the information they've already given to us. Ruhab, yes, sorry, 2 decimal places they need to be to you, right? So bearing in mind this, and we know this, yeah, good. Hussein, MiO3. That is the format that our answer is going to take, okay? So the student dissolves 1.55 grams of B in water and makes it up to 250 centimeter cubed. They love doing that, making a standard solution. The student then pipettes 25 centimeter cubed of it into a conical flask, followed by 10 centimeter cubed of sulfuric acid. Now, the reason for that is it's a redox titration. The sulfuric acid isn't reacting in any way. It's just providing hydrogen ions for this reaction, okay? So the iodate ions are reduced to iodine as shown below. The resulting mixture is then titrated with 0.15 molar sodium thiosulfate. So nice and easy to kick off with. The student repeats steps 2 and step 3 until concordant titers are obtained. Complete the table to 20.1 and give and calculate the mean titer that the student should use for analyzing. 23.8, Yasmin, all over this. Anybody not get 23.8? Okay, so this is 24.00, always to 2 dp. Watch the dps in there. Okay, so this one is 23.4, 23.75, and 23.85. Okay, so Overall mean titer, which ones we're going to use? One trial, 1, 2, and 3 out of those. Oh, Hussein, you answer questions before I've asked them. So it is 2 and 3. That's what we're going to use. Okay, so the mean titer there is 23.80. Done. Nice and easy. We don't need to talk any more about that, but you get your 2 marks, 1 for selecting the correct ones and 1 for actually calculating your mean titer, which is that one plus that one divided by 2. Okay. Now, the uncertainty in each burette reading is plus or minus 0.05. Calculate the percentage uncertainty in the titer obtained from titration 1. Give your answer to 2 decimal places. 2 decimal places. So titration 1 was 23.4. Okay, so that's 23.4 centimeters cubed. What are we putting above that? Okay. Okay, I'm going to go through it, Ella, don't you worry. Now, things to pick up on here. The uncertainty in each burette reading. When you do a titration, how many times do you read your burette? Bearing in mind, we've got a table there. Does, die, zwei, how many do you want to call it, okay? How many different languages you know the word to in? Does, yeah, absolutely, okay? Dos, ni, oh, I say I'm loving it. Multilingual Zoom room tonight, okay? Twice, yeah, thanks, Issa. So because you read it twice, each time you read it, you've got that percentage uncertainty. So because you read it twice, we have to multiply this by 2, okay? And it's the same for a balance. When you're using a top pan balance to get a mass and you do it by difference, so you weigh it, you pour whatever it is you weighed into your beaker or whatever, and then you reweigh your weighing boat. That's the same thing. You're using the balance twice. So however many times you take a reading, that's what you need to do up here. So this is actually 0.1 because it's times 2, 0.05. So that is our calculation, and we actually end up with 0.43. Okay. So has anybody got any questions on how you use percentage uncertainties? It's de is 2, do's is 12. Yeah, so it's not 12. Anybody got any questions? Give me a note in the chat if you haven't. That way I know we can move on. Yeah, so the formula is number of readings times uncertainty divided by volume. Yeah, I think you can generalize that. Number of readings times uncertainty divided by volume. Okay. Epnin, I like it, JK. I've learned something new. Every day's a school day, right? Like quite literally. That's our percentage uncertainty. So just be aware of that, okay? Now, I've seen a question. Just be careful how they're worded. The uncertainty, if they said for titration 1 is 0 plus or minus 0.05, what would you do? If that was the wording of the question. Good. Yeah, you do not multiply it by 2 because what they said was, oh, that titration, this was the uncertainty for that titration. So you don't need to multiply it by 2. Okay, so just be careful. I've seen these questions worded slightly differently. They put tripwires in the exam. Of course they do. Okay, you've just got to, because for the titration as a whole, they said this is the uncertainty for the titration. Whereas here they said for each burette reading. So it depends on the way they word the question, okay? Pipettes, you only times by once, okay? Because you don't read a pipette twice, do you? You don't read a measuring cylinder twice or a volumetric flask. You only read that once because you measure that volume and then you let it out. But a burette, you've got a starting volume and a final volume, and you read it twice, don't you? Okay. So other pieces of measuring equipment like a burette, like a pipette or a measuring cylinder or a graduated or a volumetric flask, you only need to do it once. Okay. 0 is at the top. Okay. So it goes from 0 to 50. Remember, in a burette, okay, it's 0 at the top and 50 at the bottom. You do not measure how much is in the burette. You always measure how much has been let out of the burette. Okay. That's really, really important. Okay. How are people in YouTube doing? Are you okay? I don't want to neglect you over there. Hopefully you're picking up some, you got that PDF all right and you're going along okay with these? How do you remember that? It's just a case of remembering it. I think you should have done enough titrations in school or college to know that. Okay, just ingrained in your brain. Okay, describe how a student could determine the endpoint of this titration accurately. Very quickly, guys. Yeah, good. Use an indicator. Add starch. Yeah, good. So we need to know this practical. Now, the practical here is in this titration, iodine is getting turned into iodide. Your indicator for this is starch. So in biology, they use iodine to find the presence of starch. But in chemistry, we use starch to find the presence of iodine. Okay. So because there's iodine there to start with, you put starch in, it's going to go blue-black. As the titration goes on, the iodine is going to get turned into iodide. So it's going to go. So the 2 marks here for saying to use starch indicator, and it's going to go from blue-black to white or colorless. They'll accept either there. Okay. You do read from the bottom of the meniscus. Describe and explain how the student should determine the endpoint of this titration accurately. I think it's more emphasis on this than this word here. So if they were to say, how do you increase the accuracy of your endpoint? You could say, rinse the inside of the conical flask, read from the bottom of the meniscus, add it drop by drop towards the end. Okay, those are the types of things that would increase your accuracy. But this question here, and it's difficult, they are focusing on this bit more. So how would you determine the endpoint? In other words, what are you looking for? All right, so that's what it's asking. Okay, so it's not asking about repeats. Accuracy is nothing to do with repeats. Repeats, reliability or repeatability. So the R's go together. To make it more reliable, you do repeats. To make it more accurate, there are physical things you need to do when you do each titration in order to make it more accurate. Okay, phenolphthalein wouldn't work here. This isn't an acid-base titration. Okay, so first years, this is a second year thing. I'll warn you. Okay, so this is a redox titration for second years. Okay, now I probably won't be surprised that a few of you may have done this already. But what I want you guys to do, I'm going to shut up for 2 minutes. And I want a roadmap, please. I want you to write down a roadmap, bullet point by bullet point, just like we did for this last question here. I want you to write a roadmap for what you're going to do to actually find the relative formula mass and formula of the group 1 iodate. Okay, so the roadmap is what steps are you going to take in order to find the MR? That's basically what they're asking for, is the MR. Okay, so what are your bullet points? Don't tell me in the chat. I'm going to give you 2 minutes. I'm going to time you on my really modern Casio calculator watch, straight from the 80s, all very Stranger Things. I'm going to time you 2 minutes. I'm not going to say a word for that 2 minutes. I want you to write down your bullet points. And I'm going to ask you to put them in the chat later. Do not do it now. So that's for you guys on YouTube as well. Okay, if you want the question, I'm going to leave. That's the question, but the information is in that PDF I've just put in the chat. Again, those of you on YouTube, the PDF for this, so you can see all the pages whenever you want, is in the description. Okay. So you just need to click on the link and it'll give you the PDF. No spoilers, Yasmin. You're not wrong, but I'm just trying to show you a technique here, okay? Just trying to show you a technique. Or was it a guess? Right, another 20 seconds, guys. Yeah, of course I will, Joyce. The stoichiometry is the hardest bit here. Okay, time's up. So let's see what we got. I don't see what, don't put it in the chat. I'm just going to run it. I'm just going to run through it with you. Okay. So Hamdan straight in there. Okay. So first thing, we need to find the number of moles. If we look at the question, okay, the first thing is that we've got a titration going on here. And this here, this is the reaction that's going on in our titration. Now, with the titration question, you always start with a number of moles and your mean titer. So we found that the mean titer is 23.8. The concentration of that is 0.15. So roadmap, number of moles of S2O32 minus in my mean titer. And that basically means concentration times volume. Okay, so the concentration times volume is basically 3.57 times 10 to the minus 3 moles. Okay, so I'm doing roadmap and I'm doing like the answer as well as we're going through. Okay, so the next step here, guys, what is the next step? Good, the ratio of S2O32 minus to I2. All right, and that is probably the most difficult thing here. All right, so let's go back here. So if I'm going to use red, no, let's use green. Let's mix it up. Let's go crazy. So if we know the number of moles of this, okay, we know the number of moles of I2, right? It's a 2-to-1 relationship. So S2O32 minus to I2 is a 2-to-1 relationship, okay? That's fine. But yeah, you're right. Issa, we need the iodate ion, okay? So this, the only iodine present is the iodine that got produced in the first reaction, okay? In other words, a reaction between iodide and the acid, okay? And that was just done, you know, in excess. The acid has put loads of acid in there. The only thing limiting that is the iodate ions. So what we need to find is the stoichiometric relationship between these two, okay? And that is actually 3-to-1. Okay, it's actually 3-to-1. So if we've got 1 mole here, how many moles of iodate produced 1 mole? Okay, because let's say we have got 1 mole. Yeah, we need to divide it by 3. So technically, it is to 0.3 recurring. Okay, so 2 moles of S2O32 minus gave 1 mole, meant that we had 1 mole of iodine, which meant that we had 0.3 recurring moles of iodate ions, okay? So the relationship between these two is 2 to 0.3 recurring. Can we make that a bit tidier, guys? We tell you what, we don't need to touch the iodide at all, okay? We haven't got anything in here that tells us the number of moles of iodide used at all. It's just like a vehicle for creating these. Yeah, good. 6, yeah, times it by 3. So we could say 6 to 3-to-1. And you know what? Our iodine is just a middleman, right? We're basically turning iodate into iodine and then iodine into iodide. So it's kind of like we're just using it. We're just abusing it, basically, okay? Using it as a mechanism to actually measure how much iodate is in there. This is very similar to what we call iodometry, where we try and find the amount of copper in something as well. So what we can say is that there is a 6-to-1 relationship between the number of moles of sodium thiosulfate to iodate ions, okay? So you know the iodate, okay? So basically, if you think in real terms, 2 moles of this reacted with 1 mole of that, and if there was 1 mole of that, then there must have been 0.3 recurring moles of iodate. So it's just like, you know, leapfrogging, okay? So back to the question. The next roadmap part, okay, for our mole calc was find the ratio, okay, and that happens to be 6:1 for S2O3 2 minus to iodate ions. So the number of moles of iodate ions in how much, in what volume? We're finding the number of moles of iodate ions, but in what volume? Good, Yasmin. Yeah, absolutely. And Hamdan, in 25 centimeter cubed. I always write this rather than just, oh, the number of moles of iodate ions, but in how much, in what volume? So that equals 3.57 times 10 to the minus 3. Because it's a 6:1 relationship, we divide it by 6. Okay, so that's how we get our answer there. Okay, and that gives us 5.95 times 10 to the minus 3. No, that's not right. Times 10 to the minus 3, divide by 2. Oh no, times 10 to the minus 4. Come on, Rich. I can't read my own writing sometimes. Okay, so that's in 25 centimeters cubed. Thank you, Yasmin. So the next step is we need to find, that gives us the number of moles of iodate in 25 centimeter cubed. We need to find the number of moles of iodate in 250, Yasmin, well spotted, because, okay, we need, oh, it's frozen. There we go. Oh, come on, Rich. That is the total stock solution of iodate ions. We've only used a small portion of it. We've actually found out how many moles are in 25 centimeter cubed, but our sample was 1.55 grams. That's the only other bit of information about it we've got, and it's in 250. So we do need to multiply that by 10. So the number of moles of iodate in 250 centimeter cubed equals 5.95 times 10 to the minus 3. Okay. Now, the last step, we need to find the MR of the MiO3. So how do we do that? Yeah, good. So the MR equals the mass divided by number of moles. Okay, so the mass, because we've got the initial mass here. Very often in these, the first bit of information they give you is the last bit of information you use when doing your calculations, okay? So that would be 1.55 divided by 5.95 times 10 to the minus 3, and that gives us 260.5, okay? 260.5, and that is our answer there, okay? Or to 3 significant figures, absolutely, but it doesn't actually say what to give it to. So yeah, if you wrote, they'll give you some leeway there. You know, if they haven't specified how many sig figs to use, then they will give you some leeway there. Okay. I have seen that, JK. Yeah, absolutely. I did it. It's in the exam guide. Okay. W minus the I. Yes, Rickhill, you are on it. Okay. So what we need to find is the formula of B. All right. So the formula of B. So what we need to do, we know it's MiO3, okay, as the general formula. So if we know, take away that and 3 oxygens, so 260.5 minus 174.9, which is basically the IO3 bit, okay, and that leaves us with 85.6. And that means if you look in the periodic table, that's what's left. That's the M, and that is rubidium 5 or iodate 5. Okay. Yeah, Ruhab. Yeah, absolutely. You needed the mean titer. You did need the mean titer, which is there, 23.80. So that's how I got this first bit. Okay. So the concentration was 0.15. Oops. So 0.15 times 23.8 divided by 1,000. Okay. I didn't show you Ruhab. Ruhab, you have got a PDF to download either from YouTube or in this chat. All right. I can't do any more than that. So, so again, what I would do and what I do before any big calculation question is put this roadmap out for myself, see the path through. I cannot stress how important it is that you don't just dive in with the numbers, okay? I mean, if you're all over these, if you're really confident with them, then that's absolutely fine. No problem. But if you're not, then this is just, it's like saying, right, I want you to drive to Scotland, right? But without having a roadmap. You're going to need a roadmap, right? Lay it out, bullet point by bullet point. I'm going to do this. Oh, and then, yeah, I can find that. And then I can find that. And then I can find that. And it takes you less than 2 minutes. I gave you 2 minutes tonight, but you know what? If you're on it, it takes you 30 seconds, all right? If you're well practiced with it, and then you're not going to make any mistakes, all right? It's really, really important. You forgot to note down, good thing to put in your FFS journal is that iodate minusing. Yeah, absolutely. If you forgot to take that off and find that, then yeah. So roadmaps come out of your head, okay? I'm just showing you the technique. So there's nothing in the site, in the course that actually does that. This is my technique, all right? You're not going to find this anywhere else. And if you do, then they pinched it off me, all right? Because I literally thought of this myself. So, or indeed, maybe it was some sort of like, I don't know, what is it when things evolve, similar things, but completely separately? Rich will be able to tell us, okay? So this roadmap is just a technique, all right? And it's to help you just visualize your way through this big complex calculation, okay? And that's what I want you to practice when you're doing your past papers as part of the TT method. Calculations, give yourself a roadmap. You're not going to miss anything out. And what it helps you do is show the examiner your steps very, very clearly, okay? I cannot stress how important it is that, because the examiners, they're following a mark scheme. Yes, they're chemists. They know their chemistry. It's not like they get a load of chimps from the zoo to do it. But they will be following. Marking point 1 is for doing this. Marking point 2 is for doing that. Marking point 3 is for doing that. So they're following a map, a roadmap, okay? So you lay it out on a plate for them, just like there it is. You've spent too long and you've worked too hard to lose marks for not showing a rearranged equation or, labeling a number of moles in an exam. I mean, it's schoolboy, right? I mean, you don't want to be doing that. Like I said, you've worked too hard and for too long to make mistakes like that and to leave marks begging on the paper. So please don't do it. Make it easy for the examiners to give you the marks, all right? Make their job easy and they will give you the marks. Ruhab, sometimes don't know to find from 20. It basically, if they've made a stock solution of 250, and it's usually 250 at the beginning of the question, and then they use 25 centimeter cube portion of that, yes, you're going to need to multiply by 10 to find out how many moles you've got in your entire stock solution. So if they've got a stock and they've taken a portion out of it for a titration, then yes, you're going to need to work back up to it. But if they've just started with a solution and they've used it all, then you don't need to do that. Okay, so it's about visualizing what the student's doing in that practical. Right, what are they trying to achieve? Visualize what they're doing, like you did. You've got your 250 centimeter cube volumetric flask. You've got a pipette. You've taken 25 centimeter cubed out of it. You found the number of moles in that. Well, how many moles are in the big thing? Just times it by 10. Okay. Yeah, sometimes you get a question the other way around. Yeah. I do have a bit of Scouse in my accent. Yeah, I live in North Wales, very close to the border with Liverpool. So, Right. Now, we have got 25 minutes left, ladies and gentlemen. There are some more questions in here. I'm not going to be, you know what? I will post a mark scheme for this, I think. But I'll do it in the Zoom, in the live recordings. Okay, so I'll do that. You will find my videos on most of these because some might be from 2019 papers in the exam guide. Okay, 2019 papers will be released when they're released to the public, so they're kind of primed and ready to go for you guys, but we're not allowed to release them yet. Okay, it depends on the exam board. Sometimes it's usually it's the 1st of May. Okay, Ruhab, we're getting to it, bro. All right, so what should we do? That's the question. So I wanted to talk about acids and bases. Okay. So what am I going to say here? Right. I'm going to go off this for a second. And I'm going to talk to you about buffers. All right. 5 minutes talking about buffers, and then we'll have a go over question. Yeah. Okay, yeah, it's nobody's favorite thing. Okay. Hey, Shannon, welcome to the YouTube. Thanks for coming. Shannon's on YouTube. She's awesome. She's in uni doing biochem, loving it. How you doing, Shannon? Who's that? Mia? I love buffers. Well, somebody's got to love buffers, right? Okay, so buffers, you're not going to be asked about basic buffers, okay? You might be asked about how they work, but it's all about the acid buffers, okay? We're not doing a question just yet, Nima. So if it's all about acid buffers, we need two things. We need a weak acid and we need the salt of that weak acid. So the fundamental core of any buffer question is this: your Ka expression, okay? I'm just generalizing with H plus and X minus, okay? Now, 9 times out of 10, what they're going to be asking you to do in a buffer question is this: find the pH. Now, if I asked you to find the pH, what is it you really need to calculate? If I asked you to calculate the pH, what do you really need to calculate? Yeah, hydrogen ion concentration. So what you've got to have in your mind this whole time is this expression. Done. Okay, so any question that asks you to find pH, you should read it as find the hydrogen ion concentration, because as soon as you got that, you're laughing. Okay, so that is the fundamental core of any weak acid question, or indeed what we're doing now, buffer questions. That is it. Okay, so there are basically 2 types of buffer question they can ask you. HX is the acid, so the associated acid, so like ethanoic acid, whereas the X minus is going to be the ethanoate ion, so after it's lost its hydrogen ion. Okay, so there are 2 types of acid buffer question. Okay, so first of all, you have like buffer creation questions. Okay, so what that is, oh, we made a buffer using this and this. What's the pH of the buffer we've made? Okay, so in that subsection, there are 2 ways in which they can make a buffer. Okay, number 1, they take an acid and they add a solid salt to it. Okay, so they're basically taking an acid or indeed salt solution. Okay, so basically taking an acid and just adding a salt to it. Now, it might be solid salt or it might be salt solution. Okay. For the roadmap, PVNRT questions, just to go back to Joyce's question, can we use the roadmap for PVNRT questions? I don't think you really need to, because all the marks from PVNRT questions are for changing your units and rearranging it. Okay, they tend to be, they're not multi-step. They're just like, you just need to get your ducks in a row before you plug the numbers into the equation. So it's not really that useful for that. Okay, so acid and solid salt. What you've got to know here is what's important is the volume, because if the volume changes when you make your buffer, you need to account for that. But in this, the volume isn't going to change, because our acid, that's basically volume. You've got 100 centimeter cubed of acid. You've added some solid salt to it. Okay, we're assuming the volume doesn't change. So you don't need to worry about it. So the volume doesn't change. So you don't need to recalculate any concentration of the acid or anything like that. Okay. Here, okay, the volume will change. So that means you need to calculate new concentrations. All right. Because if you take 100 centimeter cubed of acid and you put some solid salt in, then your concentrations you can work out. It's 100 centimeter cubed, that's not changed. But if you've had 100 centimeter cubed of acid and then 50 centimeter cubed of your salt solution to it, then your concentration of acid is going to change, because you've just added another 50 centimeter cubed of water to it. It's going to become less concentrated. Okay. So if you're adding a solid salt to a solution of acid, then the volume doesn't change, because you're just adding something in. It's just going to dissolve. The volume might change ever so slightly, but as far as we're concerned, it doesn't change. Okay. If you add a salt solution, so if you had 50 centimeter cubed of salt solution to 100 centimeter cubed of acid, then your volume has changed, hasn't it? Okay, because you've added 50 centimeter cubed. That means your acid concentration is not going to be the same as it was. It's going to change. It's going to go down. So just be wary of that. Just be very, very wary of that. Now, the other type of buffer creation is this. You get your acid, okay, your weak acid, which of course, is taken as red here. We're dealing with weak acids because strong acids don't make buffers, okay? And then you add some alkali to it, okay? Now, again, you will get a change in volume, okay? Depending on whether it's solid, it won't change volume. But if it's an alkali solution, again, it will change volume, okay? Now, the reason this creates a buffer, okay, is as follows. So your acid, so let's call that HX, plus your alkali, let's use sodium hydroxide because you know what, we always do. That then gives you your salt, which is basically X minus, okay, this up here. Oops, there you go. There you go. And water. So what you're doing by mixing a weak acid and a strong base or an alkali is creating a buffer solution because you've still got some HX and you've made your salt. Okay. So regardless, so what you'll find is every single time that this is in excess, you'll have some acid left over. Okay. You'll have some acid left over. And all this will be used. So you don't need to worry about that, okay? But the thing is, when you add an alkali to your weak acid, what's going to happen to the number of moles of your acid when this happens, when this reaction is going on? It decreases, absolutely. So the number of moles of acid will decrease. So you need to account for that and calculate that and find your new concentration to put in your expression up here. What's going to happen to the salt concentration or the number of moles? It'll increase, absolutely. Okay. 1 second, guys. So that's what's going to happen, okay? So the number of moles of this will increase, the number of moles that go down. So you just need to calculate it and calculate your new concentrations, okay? So when this decreases, you'll start with maybe a concentration and a volume, okay, of acid. So you know a number of moles of acid that you started with. So if you started with, I don't know, for argument's sake, 2 moles of acid, and this is a 1-to-1 reaction, and you added 1 mole of alkali in, how many moles of acid have you got left over? Yeah, 1, absolutely. Okay. So you basically just minus 1 from that and you got 1 mole of acid left over. That's it, done. Okay. So your acid's going down. You can work it out really easily by, taking away the number of moles of alkali that reacted with it. You know how many, what number of moles of acid got reacted. And of course, we know the number of moles of salt produced because stoichiometry, we get 1. Okay, so it's about balancing. You add these two things together, acid's going to go down, you've made salt, and now you've got a number of moles and therefore concentrations to put in your expression. Okay, so buffer creation questions are the first type. So let's just do one. Okay, let's just do one. So let's have a go of this one. Okay, so this is year 2's only, guys. So there's questions about weak acids. A weak acid has a Ka value of 5.25. A solution was formed by mixing 10.5 centimeter cubed of sodium hydroxide with 25 centimeter cubed of HX. Calculate the pH of the solution formed. You can do a little roadmap for this. It's up to you. I mean, do you want to have a go first? Do you want me to give you 4 minutes to have a go at this? Or do you want me to just go through it? I'll go with the majority. Okay. I think the majority of this have a go. So I'm going to give you 4 minutes. I'm going to shush and you guys are going to have a go. Off you go. Sorry. Okay, you got another minute and a half, guys. Okay, so let me stop sharing my screen for a second. I tell you what, rather than me write all this out, what I'm going to do is I'm just going to show you. 3.84, 3.842, 3.842. That's great. We've got some good kind of concordancy going on here, which is awesome. I am just going to, you know what? It's easier just to bring the answer up, I think, rather than me write it all out. So I would say that I need to find trying to find the question now, guys. One sec. Not that one. My bad. I just hate it when stuff crashes. Damn it. All right, well, I'll tell you what, let's just do it from first principles. We're going to have to. Okay, so let me share my screen again. Oh, there we go. Sorry about that. Okay, so weak acid is a Ka value of this, and that's absolutely fine. Whoops. Bring my pen up. So Ka value of 5.25, that's fine. I'm going to go back to blue. Solution was formed by mixing 105 centimeter cubed of 0.8 molar sodium hydroxide with 25 centimeter cubed of HX. So again, we've got HX reacting with sodium hydroxide to form NaX, which is basically our X minus. Let's not forget there, that's our salt, and water. All right, so the first thing to do is number of moles of acid. So that is concentration times volume. So the initial number of moles of acid. It doesn't matter. I don't care about the concentration right now. We'll sort concentrations out later. So concentration times volume of acid is 0.92 times 25. If you guys can give me the answers to these calculations as we go along, that'd be great. It'd speed it all up. Divided by 1,000. So what's that? Oh, you can't be giving me different answers. 0.023. I'm going to go with that. 0.023 moles. Okay. Now, the number of moles of sodium hydroxide, again, we can use concentration times volume. So that is 0.8 times 10.5 over 1,000 standard. What's that one, guys? 8.4 times 10 to the minus 3? Is it? Yeah. 8.4 times 10 to the minus 3 moles. Now, that's before we've mixed them together. So the number of moles of HX after the reaction, okay, because this is a one-to-one relationship, is 0.023 minus 8.4 times 10 to the minus 3, because you know what? The sodium hydroxide has taken those out of the game, right? So what's that? 0.0146. Thank you, Hamdan. 0.0146 moles, okay, of HX. The number of moles of X minus produced, so our salt, equals 8.4 times 10 to the minus 3. We've actually made that much, okay? So don't worry, if you're year one, you're not going to get it, okay? Why am I minusing again? Because we don't need to minus. This didn't exist before the reaction happened, okay? So if we know that 0.0146 of this was used, that's gone down by 0.0146. So that means we've created that much NaX, okay? So that's what we've done there, okay? So that's the number of moles of X minus produced. Now the number of moles is no good to us. In terms of our expression, if we're going to find the pH, we need this. We need concentrations of HX and X minus. So how are we going to find our concentrations, guys? So concentration equals number of moles divided by volume, right? What's our volume? Good, Yasmin. Yeah, and Joyce and Nima. Yeah, you're on it. Absolutely. Your volume, you've got to be careful of your volume because you've got two here, 10.5 and 25. Okay, so it's 35.5. You have mixed these two solutions together. You've got an overall volume of 35.5, well, divided by 1,000. Okay, yeah, that's it. So the concentration of HX equals number of moles, which is 0.023 divided by 35.5 over 1,000. What's that, please, guys? Well, Hamdan's all over it. 0.411. And then the concentration of X minus, that is 0.0146 divided by 35.5 over 1,000. And that is 0.237 moles per decimeter cubed. Always put your units on where you can. Okay, so that's moles per decimeter cubed. So what we've got now is everything we need for our expression. So Ka was 5.25 times 10 to the minus 5 times HX, which was 0.411, all over 0.237. And that is our hydrogen ion concentration, which is Any takers? I've used the wrong number of moles. No, I've not used the wrong number of moles. That was the NaOH stat. So it's 9.1 times 10 to the minus 5. Is that correct, yeah? Okay, brilliant. I'll go with that. So then, therefore, we'll sneak this in at the bottom. pH equals minus log base 10 of that, which equals SAD. pH of 4. We all agreed? I'm going to do it. Minus log 9.1 times 10 to the minus 5. Yeah, let's go with that. 4.0. Yeah, let's go with 4.0. Done. And of course, common sense check, it's an acidic buffer. So it's going to be below 7, right? He said, when you did convex minus, why did you use 0.416? Because 0. This one, x minus, no, 416. Oh, yeah, that's because it's that. You're right. Sorry, I do apologize. Number of moles, 8.4 times 10 to the minus 3. Sorry, guys. I assume that answer's the same, yeah? Yeah, okay. My bad. My bad, yeah. I used the wrong one. This is why I was going to show you one I did previously, because it was easy to explain through it. You made the wrong one for HX as well. Oh, just so easy to do, isn't it? That is 0.0146. My bad. Sorry, guys. It's been a long 2 hours, right? It's been I haven't stopped talking. So, but you get me, right? It's so easy done, especially when you're trying to explain it and do it at the same time, all right? So, you know what? We've run out of time. I just want to show you a couple of things, okay? So, this one is very similar. Here, a student prepares a buffer solution. They want pH 4.5 to contain ethanoic acid and sodium ethanoate. Basically, they've added that mass of sodium ethanoate to 250 centimeter cubed of acid. So they've added a salt, a solid salt, to an acid here. Okay, so that's why, yeah, the volume doesn't increase. JK, you're absolutely right. The volume doesn't increase here. That is your volume, okay, because you're adding a mass to a volume. Now, this one, this 9.4, this is a daddy of a question. If you can get through this one, you can get through anything. So you prepared a buffer by adding that many moles of salt to that concentration and volume of a weak acid. The student then added 3 times 10 to the minus 4 moles of sodium hydroxide to the buffer solution. Calculate the pH of the buffer solution after adding the potassium hydroxide. So this is the second type of buffer question you can get. The first two here, that one and the one we just did, they're about creating a buffer. This style question, the second type of buffer question you can get is like, we've got a buffer, but I've put some acid in it, or I've put some alkali in it. What's the new pH? So you've got to figure out what's it going to react with. So go on to the content guide, okay, and I talk you through the different types of reactions that buffer can have. All right, so acidic buffers, what can happen to them when you put alkali in there and when you put acid in there. And if you know, right, well, if you put acid in, okay, the number of moles of salt is going to go down because you're adding H minus, salt goes down, but acid goes up. If you put alkali in, acid goes down and salt goes up. So as long as you know that, okay? This particular question is not on the exam guide yet. That is all I'm going to say, all right? But I will put the mark scheme up in when the recording of this ends up in the live class registration page, okay? So within the course, this recording is going to be in there, and the mark scheme for these questions is also going to be in, okay? Yes, absolutely, Yasmin. OCR put these types of buffer questions in as well, okay, as well. So, ladies and gentlemen, I'm going to ask you to do a couple of things for me, okay? Number one is tell me, did you find tonight useful? Yes or no? Awesome. For the calcs, brilliant, okay? What about if I mean, basically we've got live classes mapped out until middle of March, end of March, something like that. After that, it's going to be bang, revision time. We're going to be looking at exam technique. We're going to be putting you through your paces in the live classes, may even do some more live on YouTube as well. So those of you who are not subscribed, keep an eye out for that. I am going to give you a code. Now, if you want to get 50% off your first month subscription to TT, okay, you can use the code that I'm going to put in the YouTube description as soon as it's finished. Okay, so as soon as I switch off, I'm going to put a code in the YouTube description. You can go in there and get it. It gets you 50% off your first month subscription if you haven't got a subscription already. Okay, so those of you in YouTube, if you haven't already, give us a like. Make sure you follow us on the YouTube channel. Follow us on Instagram as well. Our brand ambassadors are in there. They are absolutely amazing. They are students like yourself. Okay, they're literally just trying to get through. They're trying to find a way through and get the best grades possible. They're going through UCAS and everything like that. Okay. So the full prices you can find on our website. Okay, we sorry, I'm so childish. We do discounts for bundles. So if you want Chem and Bio, you want Chem and Maths, okay, always Chem. Then you can get money off that. Okay, so it is a bundle subscription for the Ultimate Guide. You get access to the content guide and exam guide, which is absolutely awesome. We're going to go a bit quiet on YouTube at the moment. On Saturday, we are doing a YouTube live. Okay, so YouTube live on Saturday, and it's basically going to be a roundup of the half-term pass, and we're going to be giving out that code as well. But again, I'm sneaking out that code a little earlier. If you want to join us for 50% off your first month, you can do that. And you know what? We're back on YouTube every single Monday answering your questions about the TT method and how best to revise and so on and so forth. Luke, you've been quiet. All of a sudden he pops up with his little 10% off code. Our brand ambassadors, like Luke, also have a code that you can use, gets you 10% off every single month. So it depends how long you're going to use it for. All right, so you can do that. Follow our BAs, follow us on YouTube, follow us on Instagram, hit the bell to get reminders about lives. Make sure you give us a like in the YouTube if you're already in there, if you haven't done so. Thank you very much, guys. Yeah, it is a bit of a shameless plug, Luke. Me and you will talk later. And don't think I didn't see you in a different live earlier on tonight as well. Me and you are going to chat later. So I'll see you guys around. I'll see those of you who are subscribed next week for some chemistry on Wednesday at 6 o'clock. Which you can register for right now. If not, then I'll see you in a Monday check-in with Ronnie on Monday. So thank you so much for coming along, guys. I literally can't do this without you because I love the interaction. You know, without you, there wouldn't be us. And, you know, we live to actually improve your grades. That's what we're here for, okay? Yeah, we need to charge for a service. We need to keep a roof over our heads. But you know what? We're teachers. And we want you to do well. And that's it, okay? We love to find out what grades you get in your mocks and your real results, that you make sure you get to the university that you're going to get to. That's what we live for, okay? So thank you very much. I will see you next Wednesday. If not, I will see you next Monday for our live check-in. Don't forget to hit the bell on YouTube and give us a like and a subscribe. All right. See you later.